very powerful concept. It applies everywhere, right? Like now I'm kind of giving a very funny example here since I'm going through it right now. I had to write code for it, so I'm bringing that over here. But it's kind of applicable everywhere, right? If you have similar images, it's nothing but a visual similarity. I don't know whether you guys use eBay. eBay has this tool where, like, you can upload a picture and search for pictures similarly, right? It uses a similar technique like this. Okay, so that is what it is. So now, having said that context out, right? Again, as every other session what I've given, this is going to be hands-on too. But it doesn't matter if you're not that technical. That's okay. Still, you can follow along from a use case perspective on what I'm doing, why I'm doing that. Uh, the code for this particular thing is open source in my GitHub. You can actually go to if you go to my GitHub, I have this code as transfer learning right out there. So the files are right in here. Okay. So if you want to take a peek at it later, you can. So let's get into this topic, right? We are going through a house hunting process right now. So that is where my requirement for this particular talk came in. And me and my wife, we have disagreements on how things are, right? How things should be and stuff. And her preference is particularly the kitchen, right? She said, like, I want a kitchen of this format. I mean, like, granite countertop, having certain things. So there's a specific format what she looks for, right? I can't really describe it. You need a picture for it. So I was thinking, okay, what can I really do to help this house hunting process make it a little easier, right? So I don't need to go to Redfin or Realtor every day and try to go through this process, click through 30 pictures to see which house actually has something of that nature, and then go look for. So that is where this thing started, right? So what for me to start with this entire thing? So what I did is I wrote a crawler to actually get data from Redfin. So when I say crawler, it's more of a scraper. Redfin actually gives you this feature where you can actually go download. So you put it in a table, and you can actually go. See the option for download all. Like if you download it, it will come as a CSV.
What are you downloading exactly?
So this is what I'm downloading. So it'll give you the sale type, whatever, right? The entire thing, whatever that was there, it'll give you the address, how many bathrooms, what the price, and it'll give you a URL for that particular house, right? So I have this information. It'll give you lateral, longitude, and truth. So, but it'll give you that information, right? So what I do is I take this as an input, then I crawl through Redfin. So this is my crawler, right? Again, ignore this part of the code. It's more of Python 3.6 has an issue with SSL certificate, so I had to include this to make sure that I can actually make a request. Otherwise, it will throw a certificate error. URL unable to open an URL certificate error. So I need to add this more of a hacky solution right now. Even the Redfin crawler can be written in a better way, but I haven't done that. I literally had to put this entire thing together in a day, or let's say 6 hours to come up with this. But what I'm doing is I'm crawling through it. I'm making sure that I'm nice when I'm crawling. I'm not hitting it at a space where it's going to do a denial of service attacks. So the crawler took almost put it that way a day to get the data. It's actually slower than a human. If it's a human, go click on it and get it is actually slower than that. That's the way I make sure it's that way. Number one. Second thing is I got all the data right along with a structured JSON. So when I say data, this is how it looks. Do you see this? So I have about, I think about 5,000 images, 4,500 documents, about 150 homes in Fremont right now. That's where we are looking, and this is what I got, right? 4,500 images. Okay, so I got that, right? So how can I actually use it to solve my problem? That is where this thing comes into picture, right? and hope it helps me to solve my problem in a little better way. So I don't need to like go do this manual process every day, right? So I can just get an alert saying that, hey, there's a home with a kitchen you like that has come out. Probably I can even put rules around it saying that, okay, this is the price point for it. Like, I can look for that particular thing. I can configure all those things, right? So that's what I want ideally for it to do. So I've crawled it. So the beauty about, so there's Andrej Karpathy is a researcher. He used to be a researcher in Stanford. Right now he's leading, then he went to OpenAI with Musk. Then he is right now leading the Tesla self-driving car team. So he made this very famous statement called, don't be a hero. Okay, that's the exact statement, don't be a hero, right? Very rarely people actually train the convolution neural nets from scratch. It's usually what they do is like, they use something called as transfer learning. That's a technique. They take that, they use a technique to get the previously trained convolution neural nets and use that for their purpose, right? So where is this really useful? I mean, like, forget about this use case for a second. Where is this really useful? Let's say we are going after building a classification mechanism to understand whether a particular image is cancerous or not, right? We are not going to get a lot of data for that. I mean, it's very hard to get the amount of data. What you can get is it's fairly like less than number. Let's say thousands. If you can get 1,000 images, that's actually fairly good, right? Or 2,000 images, put it that way. But deep learning algorithm needs lots and lots of data. So how do you do that? So ideally, what you've done is you have a prior, you've trained it for something else, but you transfer that knowledge over to here. So it learns those weights, the feature extraction, and all those things, what it has learned, right? So that's the beauty about it, right? It learns something like how to extract features, how to identify the curves, how to do all these things. So it uses that knowledge to actually extract this information too. So that's what it is. So, and again, the best part about deep learning community is it's fairly open. There's a competition that is run every year called ImageNet. ImageNet competition, what it does is it takes it's called CFAR 10. They call CFAR 10, 100, 1,000, different classes that they have to predict from images. So let's say whether it's a bike, whether it's a car, whether it's a train, you have to predict it. So the competition has been running for some time now. People have tried different architectures. That's where actually one of the first major improvements for deep learning came into picture. 2012 by AlexNet. That was the paper which came out. I talked about it in my first talk too. That's where it came out, right? Use of GPUs for computing and all those things. But what has essentially happened is you can use that. You can actually, whatever it was trained on something else, but you can actually use that and remove 2 or 3 layers out from it, and then actually use it for something else. And maybe even add your own layer, fine tune it. Make sure the other layers weights are frozen, but you can actually use it to fine tune it to use it for something else, right? It's a very, very powerful technique. So there are like very common architectures that are being used. These are the architectures which have won these competitions over a while. BCG 16 won it once. I mean, there's ResNet 50, then there's ResNet 150. There are like a lot of these architectures, right, which has performed fairly well over a period of time on those competitions. And what they've done is they have open sourced the architecture what they've used, and they open sourced the weights. I mean, since weights is what these algorithms learn, right? So all these deep learning, that's what it really learns. So they have open sourced that too. So you can pretty much download that, use it for your purpose. It comes with an Apache 2 or maybe like BSC3 license, a different licensing what it comes out with, but it's fairly good, right? So you can actually download and use it for your purpose. So what I'm going to use here for my purpose is, it's called VGG 16. Okay, that is what I'm using. Let me actually pull the VGG 16's architecture. I have a question. Sure.
So for the weights, you're still using the weights, right, from the previous architecture. So how does that useful if the previous network is training to classify something else than you are classifying?
So ideally, right, that's a good question, right? So what happens is, in the first layer, it's not going to go after trying to classify a cat or a dog. The first layer probably is going to try to identify where the ear is, or where the curve is, where the edge of particular thing is, right? So we're using something of that nature to actually use. Okay. So again, right, on another principle, nobody really knows why transfer learning works underneath. There's hardly any literature or very few literature that has been published attempting to explain why transfer learning works, but it works. Okay, so that's the truth of there. But again, the one intuition for it is it doesn't actually learn till the last layers to classify what it is. Till that point, it's more of a let's say edge detection mechanism or like colors and like whatnot and all those things. Right? It gets to that point where it can actually understand what it is. Okay, so this is a VGG. Trying to. This is the VGG16 architecture, right? You can probably look at it. 224/3. That's the input, and then like we apply a set of convolution. Then it denoted by color, right? Convolution, prelude. Then you apply back pooling. Then you have a fully connected layer, and your output is like 1000, right? Whatever. Okay. So that's what you're ideally getting out of that. You put a softmax classifier on top and whatnot and all those things, right? But that's what you're ideally going to get out of that. Okay.
So 1000 means basically you categorize 1000 different objects,
right?
Cat, dog.
Yeah, that's right. So there are different ways how, essentially CFAR10 is, but there are like multiple architectures, CFAR10, CFAR100, which means the softmax would be 100. Then there will be like 1000 is 1000, like things like that, right? There are different flavors of architecture which has come into picture. But ideally, what you do, you end up flattening it. You put a fully connected layer on that, and then you use that to deal with it, right? That's
is that number is a granularity, like when you say C4000 or C410?
No, it's the amount of classes what you have to predict, right? Let's say I give you a picture and I want you to tell whether it's a cat or dog. That's it, right? Now I'm asking you to predict 2 classes, right? So that will be 2 at the end in that case. So if I'm going to say 10, which means like I'm asking you to predict whether it's cat, dog, let's say a bike or a motorcycle or like a train. So that's what it is, right? So that's a softmax layer.
So basically the categories are like the number of categories.
Exactly. So that's what it is, right? So this is the way VGG16 architecture. VGG19 is pretty good too. So I've used both in this case. So what I'm doing is, it comes with the softmax layer, right, at the end. Yeah. So a lot of these frameworks, right, TensorFlow, Keras, PyTorch, Theano, they used to be good, but like now they're not supporting it anymore now. But there are a lot of these frameworks, right? You can actually load these weights and the architecture over, and you can actually remove the last layer or whatever layer you want to pop out, you can pop out, right? So then what happens is you just get that layer where you want to have your results for. So ideally you get just a vector output of that particular layer. You can tap onto that. You can get an intermediate output layer wherever you want to, or the last layer wherever you, so whatever. So in this case, right, the way I'm loading this particular model itself, if you look at it, model VGG16, weights, I'm saying ImageNet, include top equal to true, right? I've included the top, but I'm popping it out. I'm removing the softmax layer. So you can do that, or you can say false, and like there's an option for false here. You can do that too. Then you don't need to pop. The layers will be like little different. So it comes with or without. There are options in Keras. People use this as a initialization for a lot of whenever you deal with images, people use these kind of models to start with, so they don't need to train everything from scratch. Training everything from scratch will take a long time. Number one, needs a lot of compute power. Okay, and the way people are doing things right now is there's a fairly influential paper which came out recently called CapsuleNet. There's a blog in Sama. There's an intern, deep learning research intern called Soham Chatterjee. He actually wrote a blog about that. Check it out. Paper came out on November 7th. The blog came out yesterday, or day before yesterday. We published it. It's a literature review comparing what are the techniques. But the way things are actually happening with CNN is they are brute forcing it, right? So let's say like okay, somebody has done this, right? Like I've stacked so many books around, right? Let's say like somebody else will come back and say like you have 4 GPUs, I have 8 GPUs. Let me stack 2 more books on top of that, right? That's the way things have been at least being done now. So we are brute forcing it. We are like packaging so many things on top. But if you want to train all those things from scratch, it's going to take time and compute power, right? And you don't know how good accuracy you're going to get. So what people generally do is use this transfer learning technique. They take that and like then add your own layer and fine tune it. Like freeze the weights for. When I say freeze, it learns the weights, right? Let's say in this case I have 16 layers. Okay, I remove 2 layers. I have 14. Let me put it that way now, right? So I'm going to freeze the weights for 14. I'm going to add 2 new layers to it for it to learn, right? So I'll fine tune that alone and then add a softmax for classification.
So, in fact, last week we had a session from Jeffrey who was doing the SETI thing.
Yes.
And I asked the same question that, did you try transfer learning and why or why not? And so for their project, they did not use transfer learning,
They
but
used
then,
that.
no, they actually used the VG, they used the ResNet architecture, but they trained it from scratch.
Okay.
But then it took them 2 weeks to train. And so that's what Jeffrey was explaining, that if we would, we trained it from scratch to get that final 2% accuracy to win the competition. But ideally, he said with transfer learning, we could have done the same work in
Exactly.
probably just 2 hours. But we would have got 90% accuracy instead of 95. But that was the competition, so they wanted to do it from scratch. But for general problems, fast, quick results, it's much better to use.
Absolutely spot on, right? Again, when I'm submitting a model for a competition like Kaggle or whatever, right? I'm looking for that 0.00% accuracy to put me above everyone. Okay, I'll use every trick in the book. Okay, to get that accuracy level. It's like race cars, right? When you want to get that second slash, how do you go about slashing it? So that's where like a lot of things comes up, and I've used it. But most cases, right, for the problems what I'm going to solve, unless until my wife is really having a requirement that the granite should be of this particular pattern, right? I don't really care. I just need to find a kitchen that she find a home with a kitchen she likes, right? So for that, the transfer learning approach would work. Most cases, you can actually get away with transfer learning. Okay, first cut. If they want to really improve on things after that, right? Then you can actually go and see like if there's a business value for actually improving on it. So it takes time, effort to build it from scratch, and you don't even know whether it's going to be accurate after that, right? Yeah.
So does that also depends on how many data you have? So if you have a lot of data, you might want to train it
Exactly.
from scratch.
Exactly, right? So again, there are different driving decisions which drives the fact that whether you want to use transfer learning or not. Let's say like I have 1 million images, right? I don't care. I can actually train a model from scratch in that case, right? I don't have an issue. But let's say I don't have 1 million images. I only have 1,000. So how do I get that accuracy, right? The good part about deep learning, it learns well. The worst part is sometimes it can memorize it. Okay, so it's like we preparing for an exam, right? I'm reading this book to prepare for an exam, right? Let's call it first certification, right? And I've made sure that I've memorized every aspect of it. Okay, and then a question that comes in from the book, which is applied in nature. It's not exactly like a replica of what is being said in the book. Then I can answer it since I've generalized it well, right? I just like made sure I memorize it well. So that will be an issue, right? So when you have less things to do, okay, let's say I have only 10 pages, I can memorize. Give me 1,000, I can't. I need to understand what is going on. Same thing, right? So you need more data for generalization. So in those cases, what you do is with transfer learning, if you only have 1,000 images, then you can't deal with things. It will memorize. Neural network or deep learning system would memorize it. So to avoid that, what you do is you use the transfer learning approach. So you have a prayer which have trained on something else, but you transfer that knowledge over here to actually take it and push it forward. Yeah.
How would you determine how many layers you're gonna freeze?
Okay. So again, compute power makes a lot of compute power drives the decision in most cases, right? Let's say if I'm going to train a ResNet 150 on something, then probably I need like a 32 GPUs for like maybe 2 weeks or whatever, or 3 weeks for me to actually get a fairly good result, right? Okay, we don't have 32 GPUs, and even train in 32 GPUs, you need to make sure the gradient is, and you need like a different architecture for training too. So how many layers? First thing is compute, number one, right? The second thing is, depends on your view. You don't want to lose too much information to start with, right? Let's say I start with a 224 by 224 image. I don't want to like get it down to like 100 immediately. The gradual reduction should be gradual in nature, like it's a pyramid structure, right? Gradual in nature. If you like decrease it like this, it's not going to help. It should go up like this, and then like you put things up. So that way people learns better. So those are the design factors which goes into deciding how many layers you really want. Okay.
No, my question is how many layers, so for transfer learning, right? How many layers you want to keep from the previous?
Okay, so usually what happens is, if for stuff what I'm dealing with, I generally stop with the fully connected layer.
Okay.
And probably draw.
Here, use that. by overfitting the same thing that you described. Basically memorizing is same.
Yeah, overfitting. Yeah, overfitting. So, okay. So if I'm gonna say, so this is my con, right? Con 2D. Then I have a think of it plus ReLU, right? So then I have a max 2D. Con 2D. Max 2. Fully connected. And softmax, right? So I can have another fully connected too if I want. I'll probably have a flattened here. Flattened here. So till this point, right, you're dealing with volume. So once you flatten it, you lose the positional information. You flatten it literally like not to one vector, right? Either I can pop out here, okay, or I can go till this point, or I can go till this point. Usually that's what people do, right? I've seen cases where, like, people pop both these out and they actually train it. Flatten, I mean, really it's not much training, but if you want to pop it out and add your own max pool after that, or come up with your own con 2D, add those things, and then actually go for, I've seen people doing that too. So that's the way it is. So in this case for transfer learning, what I've done is I've popped it out here, right? I've just popped the softmax layer out, and I have a fully connected layer. So my output for this one would be 1 into 1000 for every image. Okay. That's what I'll get. Any question? Any other questions? I think it's all shape manipulation, right? That's what it goes to. Okay. So I've loaded my image right here. Question? Okay. So I've loaded my image right here, right? So you can actually see the shape. That's what I was talking about, right? One feature, like, what is the shape? It's 1 by 1000. That's what I'm getting. Image. That's what I'm really reducing an image to. 1 by 1000. So, okay, I've done that, right? Now, what I need to do is I have to go through every image that I have in that list. So I have two things here. I have like a JSON which has all the information, metadata information of like what are the images that is linked to a house. Okay, I haven't implemented that part yet. I'll implement it later tonight and put it out in GitHub. You guys can refer to it. So I have a JSON which has the metadata information. Then I have the actual image, right? So what I'm doing is I have to loop through the images and actually convert that into a 1 by 1000 for each image. That is what I have to end up doing, right? So if I have to do a 1 by 1000 for each image, so in this case I have 4500 images, right? So I'll get an array of this 4500 into 1000. That is what I'll be ending up getting, right? So this section I'm looping through. This section I'm like looping through the thing to get actually the list of files. I'm assigning it to a list, right? All the file names. And what I'm doing is I'm initializing a NumPy array with zeros here for the length. This is my number of rows, and this is the column size, right? That is 1000 where I'm getting it from 1 into 1000, right? That's my column size. So ideally, what will happen is for every, so let's say, or 02999, right? So these are the stuff, right? So I'll end up having to 4504. Okay. This is what you end up having. This is how the list would be, right? Your matrix would end up. That's a matrix size what you end up getting. So that is what actually you have. All that, right? 4504 by 1000. So that is your matrix size, right? We initialize it with 0. But what I'm doing here, right? So what I'm doing here, right? So if you look here, for counter value, what I'm doing is I'm looping through the list what I have along with the counter, and I'm getting I'm loading the image from the image path, and then I'm putting it through the model. I'm getting since I've popped that layer out already, I've disconnected it here, right? I don't have a softmax anymore. I'm not gonna get a binary answer, yes or no, or like no what it is. I'm gonna get a 1 into 1000, whatever I'm getting, right? From that, I'm assigning it to the array, the NumPy array, what I initialize it to 0 for that particular counter value. Okay, so that's what I'm doing. So what will happen is at the end, you will have, let me actually show you. That's what you'll have inside the array. That's a vector. Okay. So now you got this, right? So okay, I have this information. Now I need to find similarity. This is a very hacky code. I have to write it better. Again, lack of time. I was trying to create this presentation for today. So one of my favorite tools, Jensen. So I use that. I know it cold. So I ended up using that. So what I did is like whatever array I have, like I saved it as a NumPy file. I converted that to text, loaded it into Jensen. Okay. So now I can actually use the Jensen similarity method for me to find similar images, right? Similar vectors. That is there in the vector space. So that's what I did, right? So that is this part of the code. Okay. So that's what I'm doing here. Loading it into Jensen and load this thing into Jensen and save it, right? So I have the model. Okay. So I got this. Now I want to find what is similar to what. All right. So that is what I have. That's my purpose of this entire thing, right? I have an image. Okay. Now I need to find what I'm trying to see. 505.
Is that your issue?
Oh yeah. So what I did is I'll show you this output, and we'll run few samples through. Okay. So what I did is I wanted to find what is similar to what. So I gave this image 2505 as an example, which is nothing but the counter what I got here. I got this from underneath anyway. I can execute whichever way I want to in an IPython notebook. So I got this one, right? This is the image. You can actually pull the image out. That is my input. Okay, that's the kind of kitchen what my wife likes. So that is what I gave it as an input. Right now, what I want to do is find what is similar to that particular image. Okay, so that is what I've done here. I've got that similarity metric done here for top 10. I put it into a list again. I'm iterating through that to get everything and display it here. So this was the image, right? This was the image, right? This was the image, right? This is the one what I gave as an input. And now, so that's the image what I gave as an input. Can you guys see it?
You've got a platform.
What's that?
So this is an output.
This is an output, yes. This is an output.
This is the input you gave.
That is the input what I gave, right? I'm getting like similar images, similar images for that particular thing.
Like this one has a platform, that one doesn't have.
Yeah, but granite countertop, right? Granite countertop with this particular thing. That is what I'm specifically looking for. Okay, so that was my
And some wooden cabinet.
wooden cabinet, granite countertops. Yeah, it's a very similar nature, right? Yeah, there will be differences like like platforms and other things which will come into picture. That you can actually tweak when you have enough data to train yourself. You can.
I think you should enter that to send it to Zillow or one of these guys, because no, I'm serious, because what happens is you like something.
Yeah.
You say, oh, I wish I could see other things like this, right? And then
Yeah, let's run a few samples through, right? Then you actually see the power. And so this is my wife's criteria, right? I want a house with backyard. My criteria is different, right?
So that's easy, right?
No.
Backyard, yeah.
Again, you still have to look for backyards with grass.
Yeah.
That is hard, right? Let's actually run a few samples through and see. So that's what the similar images are, right? So fairly simple application for it. I mean, it's bringing the same thing. So
Can you stitch both, like yours and your wife's?
and yeah, finally that's the decision, right?
His wife's neural network will supersede his.
And then my son
You
comes
could
up.
probably put a weighted.
And that'll be
Put a
like
weighted
99.
Yeah, you're better, right? Yeah, probably it's going to be weighted. Yes.
But when you initially took it from the table, right, you would have images of the rooms and everything, right?
Everything. It runs on everything.
No, your input would have all the images,
Yes.
right? So the table which you showed us in the first one, right?
The 4504 into 1000.
Yeah.
Yes.
So those will have
Everything.
Everything. Right?
So this is what the input was for it, right? This is what I had.
So this will have all the images, right?
Everything, right? It in fact had like bedrooms.
Hmm.
I mean, like, no, it has everything, right?
So clearly the output is working because it's actually at least even kitchens and kitchens with countertops.
Yes.
So that's a good.
Kitchen with countertops, and actually, it's a pattern what my wife really wants, right? Kitchen with a countertop. That is what she wants. That's what she attracts. Oh, this is really good, right?
That's it.
Now, yeah, probably that is going to be a surprise, but that is what is going on. So
So are you saying this neural network can actually predict what women want?
no, no. I want
That's even more deep learning.
Oh
So
my
I-
god. That neural network, you'll be the king. If you can do that.
That is not come, that will not come.
No, I want to be politically correct here. No. But let's take a different one and run through, right? Let's actually take a different. I want to find one with the backyard. Yeah, let's take this one.
Where did you pull these images?
Redfin.
Redfin.
Wrote a crawler, got data from Redfin for Fremont. It's actually something which I'm using currently.
To
Yeah, search.
search your house.
Yeah,
That's fantastic.
yeah. It's my use case, right?
Yeah, that's.
Take a brokerage license.
No. You can sell it after you're done. Sell your software to Redfin.
Now again, public data crawl, right? So it's not going to be.
No. I'm saying software.
Yeah.
Not.
I open source it, so people can use it. Let's put it out.
That's good. Very good. You know, there's a competition going on in Zillow. Zillow has put a Kaggle competition
For
for predicting that Zestimate, right? They have Zestimate.
yeah, that
$1
just
million.
sucks.
Yeah.
$1 million if you win.
Wow.
Yeah, that just sucks.
So they have these 2 rounds.
Cut it out, please. Edit it out.
Do you believe? Does Redfin also do
Huh?
estimation? Do you believe the estimate that they provide?
It's reasonable.
Redfin users.
But what they're doing is they're saying that they
Okay.
believe that estimate.
Oh, okay.
They
both wrong.
know that it's not accurate enough.
Yeah.
So they're holding this competition. And what Kaggle is holding, and they have 2 rounds. First round, you basically like top 10 based on historical data and how well you're able to predict the sales.
So there's
And
another
then
market you are looking for.
future sales, next 3 months.
Oh, wow, okay.
Okay, so this is my requirement, right? House in the backyard.
Yeah.
Okay, so I ran the model right now.
So you have a deck and a.
Technically, I don't need a deck. All I want is like a little bit of greenery, right? See?
Yeah. Oh, that's good. Does it take Vastu and Feng Shui into account?
See, now this is where, right? Like now I'm brute forcing it. Now,
Yeah.
now it actually understood only the grass. I wanted the grass, right? So that's actually showing the front yard, not the backyard.
Yeah.
So those things actually you have to train to get it out.
There's another idea, right? I mean, you can build something based on Vastu or Feng Shui. My God, it'll be a huge hit in Bay Area at least. Right?
Let's actually try something else. I mean, you guys want to pick something? Somebody wants to come and pick some image. Let's try it.
Swimming pool, balcony,
Balcony.
home with balcony, if possible.
Home with a balcony. Let's see whether I have that image.
For patio, you mean?
Yeah,
So the
that part,
house, they
purpose.
won't have a.
That's what my mom told me.
Yeah.
When we were in her house.
He's Purpose.
Fireplace.
Lots of people live in
You?
Ignorance is bliss.
but that's they're happy.
Yeah, but it doesn't give you much, right?
Large symbols, big ones.
Right. If there's the hormones already.
Just zoom out, pinch out.
Good job.
Now after breathing.
No?
It doesn't give you enough. I'm looking for something. Maybe you have to come and choose one here in the image.
Still holding on to that.
Check out if we can find a pool, that'll be easy.
Maybe it's right.
I haven't seen one. I mean, like, that's going to be very hard. Finding a pool.
Food and Fremont.
Education.
Yeah.
So you're supposed to.
I have to hear it all the time.
Really?
I know.
Actually, pool, balcony,
Sure.
backyard, these all can be structured data.
Yeah, it is, right? But
I don't, that is a metadata, we already have it.
exactly. This case is a little different.
But you're not
What you're
using it.
looking for granite pattern, that would not be metadata, that requires more,
Exactly. I'm trying to find one that I can actually run some other example.
Coincidences there? Exactly.
Trying to see which one I can use.
Something good happens, you see them, it's working.
Bedroom with a window or something like that.
Something bad happens, you
It
say.
was for a pool, right?
yeah.
But that one's enough.
Okay.
It's a pretty big pool.
Yeah, it's a
Probably
probably
not
like.
like
Image is not-
Community pooling.
I'm looking at which one.
There's a community grass area.
Oh, this is smart, actually, this is something that probably, see, most of the good ideas come from your personal need, right? Like that you're trying to do something that you feel, well, good thought, very good thought.
I'm going through it right now, right? So
Yeah,
I have to solve that problem somehow.
Exactly. That's but not the best algorithm can do that. So she's saying, can you write an algorithm to find a good house for less than $1 million in Beijing?
Again, right? It's subjective, right? Not objective.
So what is that 2205 you have given? It's an image
No,
number.
it's image number. No, see, that's the problem, right? It's not
Anything that blue is picking up.
found. Yeah, anything with blue it's picking up, and it is bringing up the pool. One or two cases. Yes,
Yeah, fools are there.
not bad.
Not bad.
So yeah, that is the talk, and that is the use case.
What is the library name?
Keras. The code is open source, so you can actually take a look at it, download it, run it yourself. You can play with it. If you monetize it, let me know. Okay?
It's put on GitHub.
It isn't GitHub. I've sent a link over.
So is there an actual use case when come to think of it? Wouldn't there be an actual use case where you say, oh, I really like this house, I couldn't afford it, or I don't know, this house is gone, or whatever, right? Now I take a few pictures which I will feed it to the net and say, find me every house which
Exactly right.
looks like this.
We have some patterns which we like. Okay, like a backyard, right? Let's say I'm looking for something very specific in a backyard with certain setup, right? And that can be really put as a metadata information in search, right? It's not structured. That's where these kind of algorithms comes into
Not
picture,
everything can be
right?
structured, yeah.
So this is more of like the reason why I use this is like it's publicly available data. I can actually demo the power of it. But if you look at from a use cases perspective, right? Anything that has to deal with images with visual similarity, you can do with this approach, right? It's actually the same algorithm, just plug a different data in. It's pretty cool, right? You don't need to train it. Since already somebody has trained it and gave you the weights, you can actually just take it and run with it.
Yeah.
So
So what's cool, I think, is you no longer have to go to a Google and say, do image similarity. It's not somewhere out there. It's democratized. You could do it yourself with simple, probably what 6 hours you took, I guess. So
yesterday.
Wow.
it's like pretty cool that we can do, and then you can put this on top of any use case and any image use case. Becomes pretty
Well,
useful.
the whole thing I like about this is that this is solving an actual problem that a lot of people will face or do face, right? And all Malay is doing is connecting the dots.
It's way more than that.
Absolutely.
Yeah.
That's a good thing,
I'm
right?
making it very simple because it's 6 hours only, right? But of course, there is
obviously.
That's why you see such a buggy code, right? I mean, like, otherwise, if I give one, it should have already taken it and ran with it. Now see, I'm copy pasting it. That I don't like.
So will this work on the MRI images or the
Yeah, it will.
Icom
It
images?
will, it will. In fact, like if you look at all these new things that are coming up, I mean, if you read Hacker News or whatever, say like, oh, we can predict pneumonia better on chest X-rays or MRI and all those things, right? Most of the models are initialized with like an image net model, some form of the other. Okay, they take that and then they tune it. Like that's the way it is. It will work.
Okay.
Works fairly well.
Sure.
In fact, that's where they're using it in medical applications. Like seeing if a tumor is cancerous or not, things like that. Where any you give it a bunch of images, but you train it from past data, and now over the period of time it can actually predict better than I guess humans.
I look for this. This is what I look for. I wanted a pool table, right? Or like a homes with pool table, or like some sort of pool facility that's out there, right? So that's what I look for.
You have to put.
Yeah, even the color didn't matter.
Color doesn't matter, but yeah,
It's pretty cool.
probably the same image, but yeah. Cool.
Even when there's a pool table in the right
Yeah.
corner, it's speaking.
Yeah.
Pool table and a car.
So again, I don't know whether I'm going to be successful using this to buy a house, right? But it's going to probably make it a little bit pain-free. Since if I have to look for some of these things, it makes it a lot easier.
Yeah, instead of going through every single listing and finding out, hey,
Yes.
where is the kitchen picture? Where is the
It's very stressful, right? Every day if you have to look at it, I mean, like it's very manual, it's very stressful. So, yeah. So, yeah. Okay. So the code is out there in GitHub.